Okay, welcome to the prep video for section 4.4. We're going to be talking about sketching curves, and then 4.5, just a little bit of that section on absolute, max, and min, because it ties in with graphing. Okay, so let's think about some things that we know already. We already know that we can get a lot of information from f of x, just the function definition itself. We can look at intercepts, x and y, asymptotes, domain, what else? If we have asymptotes, it could be vertical or horizontal. A lot of information here. We can get information from f prime. That tells us what the function is doing. Is it going up or down? So we can get increasing, decreasing, and max and min. And then, from the second derivative, we get a sense of how it curves. It's not just going up, but maybe it bends a little. So we can get concavity and points of inflection here. So if we put all of this together, we can use, by plotting all of the important points, we can, sketch the curve and have a very good idea of what it looks like. So we have a process then. I'm going to write it over here. So this is called analyzing the graph or the curve. And so the first thing we're going to do is we're going to look at these three pieces and get particular information. So from f of x, the first thing is always domain. And then remember, if you have a rational function, you're going to want to factor top and bottom to see if anything cancels, because those will be holes in the graph as opposed to asymptotes. So domain, if it's, and then always, the y-intercept is always the easy one to find. You just put in x equals 0, the x-intercept. And then if you have a rational function, both vertical and horizontal asymptotes. So that's a lot of information we can get just from the function. And then from the derivative, we'll get areas of increasing and decreasing, and we'll get any max or min values. It's important when we start writing down this information to write all of our points in xy pairs, so that way when we go to graph, we know exactly where the point is. And then anything like an asymptote needs to be written as an equation, x equals or y equals. Okay, and then from the second derivative, we'll get concave up and down. Anytime we're talking about regions, we're going to go ahead and use, I'm trying to say, the format where you lost myself. And then inflection points. Interval notation, interval notation for regions. And so once we have this, once we have our graph, then we can go and look and see where the absolute max and min are. So let's talk about that. So absolute max and min are different from local. Local max and min we can get from the derivative. And so if we know that a function looks like this, we know that here we have a local max, because in that area it's the highest value, and here we have a local min. Okay, but neither one of those are the absolute max or min. And the important thing about this is that we need to look over the entire domain, or if it's limited, we'll get to that next time, we can look over a very specific interval. But so here, if we're looking over the entire domain, we want to look for the value that is the highest. Importantly, this is a concrete value. It is a number. So because of that, infinity does not count as an absolute max or min, so it cannot be infinity. And because it is a specific value, it can't be a horizontal asymptote. You can't look at something, or an oblique asymptote. It can't be approaching. So not infinity and not at asymptotes. Okay, so that means a function, in this case, there is no absolute max or min, because the absolute min is headed towards negative infinity, and the absolute max is positive infinity, and neither one of those count. So this one, we would say, has no max or min. You could think of, your basic parabola. Clearly, that's the absolute max. The graph does not go any farther than that. So you can have one or both, or neither. So we need to remember that. So how do we find these absolute max? Local max and min come from the derivative. Absolute max and min come from the graph, with the caveat next time we're going to look at what happens when we restrict the interval. So it's not the entire domain. Okay, so let's look at a couple examples. I'm going to leave kind of our directions over there so we know what to do. I should warn you, these problems, while they are not difficult, they have a lot of steps. So make sure to just leave some space. Don't feel like you're gonna, it may take a half a page or even a whole page to finish one of these. And again, it's not because it's hard, it's just there are a lot of steps. So let's start with this first one. F of x equals x cubed minus 6x squared. Okay, so we need to get our information that we can find from the function itself. So what do we know? We know that, and I like to actually kind of keep a running list off to the side, so I'm doing my calculus work here, and I'm keeping a running list of important information here. So let's start with domain, polynomial function, so we know all reals. Y-intercept, always easy because it is x equals 0. Put that in here, we get 0. X-intercepts, okay, that comes from where we set this equal to 0. So that means we're going to need to factor out. That will give me x equals 0, and this will give me x equals 6. So clearly this is one of our x-intercepts, 0, 0, but then we also have 6, 0. No vertical asymptote, no horizontal asymptote because it's a polynomial. So we've gotten everything we can get from the function definition itself. So now it's time to look at the first derivative. That's an easy one, all powers. I have to say that polynomials work out very nicely to go, to the second, and even later when you need to go to a third derivative. Rational functions get messy quickly, so we're not going to do as many rational functions as I would like, just because they get very tedious. But so we'll do more on polynomial, but some rational. Okay, so what do we do? What do we do here? Once we're at this point, we found our first derivative. We need to set it equal to 0 because we need to do a sign chart to find out where it's increasing, decreasing, and where our max and min are. Okay, so it's a polynomial, so we're going to factor. You always factor out first the things that are common. So 3x, x minus 4. That one gives you 0, and that one gives you 4. And these are actually points on the graph, so we can give them points. We'll test some values. So maybe negative 1, 1, 5. Negative 1, negative times negative. 1 would be positive times negative. 5, positive times positive. And I didn't leave enough space on the board because I was hoping to get it all here, but if you leave an extra line, you can actually write in some arrows. And that kind of helps you it gives you a sense of what the graph is doing. So let's transfer information from this into our list of important information. So we need to know when it's increasing and decreasing and what the max and min, local max and min points are. So we know that this is increasing out here and out here. So negative infinity to 0 and 4 to infinity. And it's decreasing in the middle. We do have both a max and a min. We have a max goes up, comes down, so we have a max at 0. You need the y value for that. We've already done that work, so we already know that that's 0. We have a min here at 4, coming down and going back up. So we need to come back and plug 4 into here, which I've already done. And I get negative 32. Sometimes you get big numbers. And so when we go to graph, we'll have to be kind of, we may not be entirely careful with our vertical axes just to be able to fit it on the page. Okay, so we've gotten everything we can get from the first derivative. So here, this is from f of x, and here from f prime of x. And as I mentioned before, let's go ahead and label that sign chart, because sometimes when you go back, you're going to have a lot of work on the page. This will help you remember which one this is. Okay, so now second derivative, 6x minus 12. We'll get x equals 2. Again, I kind of like to factor it, even though I can see it's x equals 2. I just find it easier when I'm doing the sign chart to have the factored form. That's kind of a preference. All right, so 2. So we'll test 1 and 3. This is our second derivative sign chart. Put in 1, I get negative. 3, I get positive. So this tells us that it's concave down and then concave up. And so that changes it too, so that's our inflection point. So writing all this out. Concave up. From 2 to infinity. Concave down. On the other half, negative infinity to 2. An inflection point at x equals 2. And again, we need to come back up in here to plug in to get our y value, which is negative 16. So this is all of our information from the second derivative. Okay, so we are ready to put together the graph. So I think I'm going to erase this so I can leave that and that. Okay, so here is where we start labeling all of our points. So let's look at what we need to go out as far as 6 for x and into the negatives for y. So 1, 2, 3, 4, 5, 6. Maybe I should have. All right, so let's just call this minus 16 and minus 32. That could be kind of tough. Let's see. So let's just start graphing points. We have a point here at 0, 0. 6, 0. We have a point at 0, 0 and 4, negative 32. And an inflection point at 2, negative 16. And now when I'm thinking about this myself, I tend to sort of either in my head or on paper kind of lightly sketch in the increasing, decreasing part. And then once I've kind of got the rough idea of what the graph looks like, then I can start to bend it and curve it the way that it needs to go. So here it says that I'm increasing, going up here, and then I decrease all the way down to this point at 4, and then I increase again, coming through this point at 6. So that's kind of what it looks like. We know it's a polynomial, and so you could probably even sketch in, you know how it curves. But let's put it together. So over here it says that it's concave down all the way to this point here, your inflection point. And if you want to, point of inflection, go ahead and maybe label it. So that means that we're going to be concave down, so we're going to be curved down until we get to here, and then it starts swinging up. And so we don't worry, you know, I didn't get through my point, that's okay. I'm going to fix that, and you can do that. So this is what we expect, right? This is what we expect a graph of a polynomial to do. It's a third degree. So that's the shape that we would expect. Okay, so let's look at an example of a rational function. One thing I'd like to point out about polynomials, when we're trying to find x-intercepts, you may run across a case where you don't know whether it factors or not. Remember that you can always look at b squared minus 4ac. That's called the discriminant. That comes from using the quadratic formula. Negative b plus or minus the square root b squared minus 4ac all over 2a. If you look at this, break it apart, we have this. Here's your vertex. And then to get to the zeros, because we know that it's symmetric about that line through the vertex, I either go plus some amount this way and minus some amount this way, and that will give me my 2 zeros. That assumes I can find that. So if you check this and it is less than 0, that means you're trying to take the square root of a negative number. So if you have this, then you know that it doesn't factor. So I just throw that out there because sometimes we run into that with polynomials. Okay, now we are ready for rationals. Now, as I said, the thing about rationals is you definitely want to make sure that you get the domain first, but then see if there's any canceling to do from numerator to denominator. There won't be for this one. This will be an easier one. So here's example 2. F of x equals x over x plus 3. Okay, so clearly we're looking at quotient rule, yay. Before we do that, let's look at information we need to get from f of x. Domain. We know that x cannot equal -3. That would make the denominator 0. You could write that in interval notation. That's just so much briefer that I'm fine with that. We also then know, because there's no canceling that can happen here, that this is a vertical asymptote. Go ahead and write the equation for that. We also know that there will be a horizontal asymptote. So that's where let's work back to our limits. Horizontal asymptote is what happens when x gets really big. Well, when x gets really big, the 3 doesn't really matter anymore. So that means that I can look at just simply the leading terms. So even in a more complicated rational function, just take the 2 leading terms. And then go ahead and do the simplification. X over x is 1. Limit of 1 is 1. So the horizontal asymptote is y equals 1. All right, what else can we get? Oh, intercept. So y-intercept, plug in x equals 0, 0 divided by 3. So 0, 0. X-intercept, well, that would be where this is equal to 0. It's the same point. So this is the only point. Okay, so that's a lot of information that we can get just simply from f of x. So we're done there. Now we need to move on to f prime. So f prime of x, quotient rule, bottom times derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Let's clean that up. We're going to get x plus 3 minus x, so altogether 3 over x plus 3 squared. Okay, so remember for sign charts, we're looking for anywhere the numerator changes sign or the denominator, anywhere either one of those is 0. So here we're going to have negative 3. But let's look at this. In fact, we didn't even necessarily need, well, yes, we did. This is positive, and when we square something, it's always positive, except for this place here, which is actually a vertical asymptote. So I'm not going to put a dot there because there isn't one. So, but it means that if I put in a value in either place, because it's squared, these will be positive. So this function is increasing all the time, but not through the point negative 3, because there is no point at negative 3. So we know that it's increasing from negative infinity to negative 3, together with negative 3 to infinity. There's no max, there's no min, there's no decreasing. So this is all of our information that we can get from f prime. Okay, so now we need to look at the second derivative. I prefer this form for substitution, but I prefer this form for doing derivatives. Then it's just a power rule. I don't have to do quotient rule. Okay, so let's do the power rule. Negative 2 comes down, so negative 6 times x plus 2 cubed times, this is not a plain x, so we do have to say times the derivative of the inside, which in this case is just 1. All right, so let's clean this up. Oh, I'm sorry, that's a minus 3. So negative 6, and again, because I'm going to be doing substitution, I'm going to rewrite this with positive exponents, so it will be negative 6 divided by x plus 3 cubed. Okay, so we have the same negative 3. Now, because it's cubed, its sign will change. So now we actually do need to check points. So negative 4 and negative 2. So if I put in negative 4, I'll get negative 1 cubed, that's negative, another negative, positive. If I put in negative 2, negative 2 plus 3 is 1, 1 cubed is positive, negative 6, negative. So this is going to look something like that. Okay, so let's write out that information. So we know that we have concave up from negative infinity to negative 3, concave down from negative 3 to infinity. Do we have a point of inflection because the concavity changed? We don't, because remember that's a vertical asymptote. And here I am not doing what I told you to do, which is to label your sign charts. Okay, so this is all the information then that we can get from f double prime. Okay, so let's start looking at what this graph will look like. We don't have a lot of points, do we? We have some horizontal and vertical asymptotes and a single point. So let's go ahead and get them all on. There's the point, horizontal asymptote. Oh, That would have been a -3. Horizontal asymptote at 1. Vertical asymptote at -3. So, now what do we know? We know it's increasing the whole time. So let's think about this. Could I be down here and increasing? No, because I'm going to run into my asymptotes. So it can't be here. So on this side, right, because it's increasing on the negative side of -3, it can't be down here. It's got to be up here. So let me just kind of dot that in. It's got to be doing something up there and curving to meet the asymptotes. On the other side of -3, it's also increasing. Well, again, it can't be increasing here because I'll run into asymptotes. So again, it's got to go through that point. So we've got kind of those, and now we look at concavity. This side is concave up, which is good because that's going to bend this toward the asymptotes. And this one's concave down, so that's good. It's going to bend toward its asymptotes. And so that's the graph. Okay, so I think that's it for the prep video. So go ahead and work on the problems. I think I only gave you 3. Each one's a little bit long, that's why there are only 3, but go ahead and give those a crack and make sure that you set out your information, labeling points as x, y, asymptotes as equations, and using interval notation for any intervals you need to specify.